Hello everyone, welcome to the introduction video of SHAARP. In this video, I will talk about the dipolar second Harmonic generation, also known as SHG, which is a widely studied nonlinear optical phenomenon. Also, I will introduce the SHAARP, a powerful package with advanced SHG modeling that addresses several key challenges in the field of nonlinear optics. The advantages of SHAARP include capability of both numerical and analytical analysis, comprehensive anisotropy and baryon fringence, and compatibility with materials with strong absorption and dispersions, to name a few. Before getting complicated, the first question you may wonder is, what is light? Here's the spectrum of light. The wave nature of light spans its wavelengths from kilometers down to angstrom, and those waves have been widely applied in multiple applications, depending on their wavelength. For example, microwave have been used daily in our kitchens and also for communications such as 5G. X-rays are used for medical detections and research purposes. To suit the desired application, a coherent light source that generates certain wavelengths is essentially critical. A few coherent light sources used in the visible and infrared ranges are summarized in the right figure. The upper part shows the material used for the coherent light source, and their corresponding wavelengths are summarized below. For example, KTP provides central wavelengths of 532 nanometer in the visible range, while the carbon dioxide laser at the tail of this spectrum generate light centered at 10.6 micron in the infrared range. You may notice that the mediums that generate the coherent light source are limited, and their wavelengths are rather narrow and thick. Then, is there a way to have a tunable wavelength to meet the broad interest across the spectrum? The answer is yes, and the solution lies on the nonlinear optics. With the aid of nonlinear optical effect, you can achieve a tunable wavelength from nearly 200 nanometer to 50 micron using 800 nanometer. Such a range can go even broader depending on the selection of materials. So what are the nonlinear optics and second Harmonic generation I mentioned? Looking at the definition of polarization, it depends on various orders of induced electric fields. Nonlinear optics is a summary of all the related effects that depends on a quadratic or higher order of electric field. Second Harmonic generation is one of the second order effects that converts waves at omega frequency to 2 omega frequency, as colored in blue rays. There are two common ways to represent such an effect. One is the energy diagram. The material absorbs 2 photons at omega frequency and emits 1 photon at 2 omega frequency. The other way to represent the effect is the mathematical form. The polarization at 2 omega is generated by combining 2 electric fields at omega frequency. The chi2 is a nonlinear susceptibility describing the efficiency of such conversion. It's a 3x3x3 tensor that has 27 components. However, it can be simplified to 18 independent coefficients using Voigt notation. SHG has multiple applications such as wavelength conversion, polar ordering detection, and pulse diagnostic. The current study of SHG are mainly twofold. One is the analytical approach that derives closed form expressions. Such a way is critical to connecting experimental observation to the fundamental properties. Common models include Maker fringes, Bloombergen and Persian formula. The other approach is the numerical approach, such as COMSOL or MEEP. Those methods are important in simulating a complex system, but have to rely on established problems. SHAARP package stands for second harmonic analysis of anisotropic polarimetry. The SHAARP package will include both analytical and numerical approaches. It can also generate closed form expressions of a single crystal or a heterostructure. This package can not only be used to study new materials to explore their SHG properties, but it can also perform anisotropic designs based on known materials. Some detailed features will be covered in the next slide. SHG modeling is a complicated process because it is a three-way mixing phenomenon as compared to linear optics. A comprehensive model is thus very important to accurately connect experimental observation to fundamental properties of materials. Multiple key factors can complicate the modeling process. The current established method mainly focuses on linearly polarized light, fewer optical axes, crystal structure with high symmetry, transparent medium, dispersionless system, and simple orientation of the nonlinear medium. Therefore, considering all these limitations in the current field, we introduced the SHAARP package, which can deal with all polarization state of light, multiple optical axes, full symmetry consideration down to the triclinic system, the inclusion of the absorption, any dispersion properties of materials, and arbitrary orientation of the medium. With all the advanced capabilities, we aim to keep SHAARP as simple as possible, and we developed a user-friendly GUI. The panel shown in the middle is the simulation page of SHAARP. The left part is the input panel that allows you to input materials properties. The right panel is the output panel that will generate either numerical or analytical results. In the input panel, we have divided into several sections. The first is numerical or analytical method. The next section is the experimental section that allows you to modify incident angles, polarizer or analyzer, and ellipticity. The following section focuses on symmetry and orientation, dielectric tensors or refractive indices at both omega and 2 omega frequencies, and SHG properties. If you don't know all the values, don't panic. We have prepared case studies that help you to navigate through some common materials. Also, analytical expressions do not require all the input, and you can obtain analytical form instead. Finally, I'd like to share a few more useful resources with you to help you better navigate through the SHAARP. You can find the package on GitHub. You can refer to detailed methods and descriptions on the documentation page. If you have problems with SHAARP, you're welcome to check the Q&A page or leave feedback on GitHub. With that, I would like to thank you for your attention, and I hope you find SHAARP useful for your research. Thank you very much.